Welcome along. My name is Dr. Alan Wood, and I'm delighted to welcome you along to the second of these short videos called In Search of the Northern Lights. If you haven't seen the first one yet, make sure you have a little nosy at that first. It's on the same YouTube channel as you're picking up this video from, because this follows directly on. Okay, so what I'm going to do, I'm going to share the screen and we're going to have a little look at the PowerPoint that we're going to be thinking about today. So I'll just amble over here. So, last time we started off talking about the Northern Lights. So we've got these beautiful bands of green and red and purple that have absolutely fascinated people for millennia. And you see them hanging in the night sky like this. These beautiful swirling curtains of colour. And they're one of the most phenomenally beautiful of all natural phenomena. So last time we started off talking about some very ancient observations of the Northern Lights. We were also talking about how the ultimate source of the Northern Lights is the sun. And I'm just going to also recap with this little video from NASA's Scientific Visualization Center. So here we can see the sun, and we see the solar winds flowing out from the sun into interplanetary space. It's a little bit tenuous, but it's still there on the screen. And then over here comes the Earth with its magnetic field. And its magnetic field shields us from most of the material coming in from the solar winds. But the shielding's not complete. Some of this material gets trapped, it hurtles down into the upper atmosphere, and it crashes into the upper atmosphere. There's two processes going on: ionization and excitation. The process of ionization creates a plasma, and we'll talk about that in subsequent sessions. Excitation creates the Northern Lights. So that led to a question that I posed at the end of last session. What colour is the aurora? What colour is the Northern Lights? And I gave you this energy level diagram here. And I said, well, let's suppose we've got an oxygen atom sitting there quite happily in the upper atmosphere. And I've just drawn its outermost electron here. This material hurtles in from space, crashes into the oxygen atom. The electron goes to an excited energy state, and after some amount of time drops back down again. And I've drawn that on an energy level diagram here. And just for convenience, I've said let's just say that 0 electron volts on this diagram will be the ground state for that particular situation where we've got the electron just sitting there in its ground state. And so I said this formula might be useful. E equals hc over lambda. E is energy, h is Planck's constant, c is the speed of light in free space, and lambda is wavelength, all in SI units. So what can we do? How can we address this question? So the first thing we can do is we can then rearrange. And if we rearrange, we can say that lambda equals hc over E. So we can now calculate a wavelength based on a change in energy. So we said our electron is going to go up to this excited state, and after some amount of time, it will drop back down to the ground state. So let's suppose it does this. So we can start to put the numbers into our equation. We can put in a number there for Planck's constant. We can put in a number for the speed of light in free space. We can put in a number for the change in energy. So the change in energy here is between 4.2 and 0 electron volts. So I put those numbers in here for the change in energy, then multiply it by this conversion factor to change it into joules. And we get 297.2 nanometers. So I've used an approximation here because exactly what number you get depends exactly how you round these various numbers here, but it's going to come out at something close to 297 nanometers. Now, your eyes cannot see 297 nanometers. This is in the ultraviolet part of the spectrum. And yet we see the Northern Lights. So what's going on? Well, what I've also done is I've added an intermediate state here. So when this material hurtles in from space, crashes into our oxygen atom in the upper atmosphere, and the electron goes to an excited state, it doesn't go to the first excited state. It goes to the second in this case. And because it goes to the second, well, it could drop down directly to a ground state, or we could have a two-stage process. So let's calculate the change in energy and the wavelength for each step of this two-stage process. So let's first of all deal with this situation here. We're going to go from this 4.2 electron volts to 1.97 electron volts. We put in H, we put in C, just like before. We put in our energies, we put in this conversion factor, and we get something close to 557 nanometers. And that's green. So it's sexy green northern lights. And the images I showed you a few moments ago show green northern lights. That's nice, it all seems to tie up fairly nicely. What about this next transition here? Well, to go from 1.97 electron volts back down to the ground state. Again, we put in H just like before, we put in C just like before, we put in this change in energy just like before, and this conversion factor. And we get approximately 630 nanometers. And that's right. So we get green, we get red. Now, the images I've shown you so far show northern lights are mostly green, a little bit of red sometimes, but mostly green. There's also a bit of purple in there as well. The purple is to do with nitrogen, and we have the same process going on as we've got for oxygen going on for nitrogen. I'm focusing here on oxygen because at these altitudes, it's more common for oxygen to ultimately be responsible for the observations of the northern lights we make. So we're going to focus on oxygen here. But still, we've got this route here, 557 nanometers, 630 nanometers, a two-stage process. You'd think we'd see just as much red as green northern lights, and we don't. That's because we need to consider a number of other things. We need to consider the sensitivity of your eyes. Now, your eyes are the most amazing optical device. They contain 6 to 7 million cones. And these cones are for detecting colour. There's more green cones than red cones than blue cones. And when we look at the sensitivity of individual cones, well, we get something that looks a bit like this. We've got wavelength on the x-axis and just a relative scale on the y-axis to show how sensitive these cones are compared to one another. So actually, down at the blue cones have the greatest sensitivity at a particular wavelength at 450 nanometers. The green cones are not quite as sensitive at their peak, but look, they spread out over quite a large range. And here's the red cones here. So you can see the sensitivity of the blue cones, the green cones, and the red cones. What you can also see is they're not just sensitive to one wavelength of light, but to a range. Now, we've said there's more green cones and red cones than blue cones. So what about the overall sensitivity of your eye? Well, if we look at the overall sensitivity of your eye, we've got that in this right-hand plot here. Here's overall sensitivity on the y-axis, and here's wavelength on the x-axis. Look at this. Your eyes are most sensitive to colours closest to green. So that is one key reason why we see more green than red, because your eyes are more sensitive to the green light. Incidentally, your eyes, of course, don't just detect colour, they're really good at detecting grayscale as well, which is kind of like black and white, but going through all the different grayscale levels. So your eyes have 6 to 7 million cones for detecting colour, but 75 million rods for detecting grayscale. Now, sometimes people report seeing grey northern lights. There is no transition that results in grey northern lights. But what it can be is if the northern lights are really faint, then there might be green northern lights present. Too faint for you to see in colour, but bright enough for you to see in black and white. So your eyes are the most amazing optical device, most sensitive to green. That's one key reason why we see more green northern lights than red. There's another reason. The second reason is it depends upon the lifetime of the excited state. So, when this material hurtles in from space, crashes into the upper atmosphere, excites these oxygen atoms, we said that after some amount of time, not very long, but some amount of time, they go back towards the ground state. So what's the lifetime of this excited state here? This excited state at 4.2 electron volts is about 110 milliseconds. That's not terribly long. So within that time, there is a chance that our oxygen atom will collide with something else. If it does, then the extra energy, this excess energy, is lost as heat rather than being re-emitted as light. And the collision can let the oxygen atom go back to the ground state. So if a collision happens in that 110 milliseconds, we don't get northern lights emitted. Instead, the energy is lost as heat. But 110 milliseconds isn't very long, so the chance of that happening is relatively small. The lifetime of this excited state here, this intermediate state, is 0.75 seconds. When we're talking about the lifetime of states, this is absolutely colossal. Therefore, there's a really good chance that in that 0.75 seconds, our oxygen atom will collide with something else in the atmosphere. And this excess energy will be lost as heat rather than as light. So we've got two reasons here. What we observe depends upon the sensitivity of our eyes. It depends upon the lifetime of the excited state. So you can see here, we've got a shorter time before the green transition, before green is emitted than before red is emitted. So that means we'll have a smaller chance of collisions before green is emitted, so a greater chance that the green light is actually emitted in the first place. So we've got more green light emitted in the first place, and our eyes are better at detecting green light. There's a third reason as well, and that's to do with the energy of the precipitating particles, the energy of the particles streaming in from space. And that's something we're going to talk about in a subsequent video. So this brings us on to another question I want to pose, or another couple of questions. We can see this beautiful image here, looking at the northern lights from a space shuttle. And so you can get a fair idea of what the height is of the northern lights by looking at them from space. However, we can work out the height at the base of the northern lights. So this sort of point down here from ground level. And I want you to have a think about that. See if you can sketch it out. See if you can work this out. How can we find the altitude of the base of the northern lights from ground-based observations? I'll give you a clue. It's all to do with trigonometry. So see if you can think about that. And you might need to think about multiple observing stations too. Then in this image here, you can see the red northern lights is at a greater altitude than the green northern lights, and that's fairly typical. So the second question, why does the red aurora typically occur at greater altitudes than the green aurora? Okay, so two good questions there for you to have a think about. Thank you very much for joining me today. Thank you very much for your attention. We will pick this up again on Tuesday next week. I hope you have a good weekend despite all the difficulties at present, and hope to speak to you on Tuesday. Thank you very much.